So in today's class, we will be talking about examples, how and where you can actually find the hardware in the loop approach. So far, we have been doing the models in Simulink, and we have used the Nucleo board only as a signal generator. And in this talk, I'd like to show you the real-world examples where you can find the hardware in the loop approach. What does it mean? I already explained to you several times what hardware in the loop means. It basically means, and I will probably explain it some example. It means that you have a model that runs somewhere in the hardware. So for example, let's imagine that you have some battery management system. You want to charge some batteries somewhere, and your task is to develop such a control system that will be able to control your application. So for this you need, for this particular example, you need of course the batteries, and you are developing a controller that will measure, for example, the voltages in the system, will measure the currents, will calculate the state of charge of your batteries, and that will also protect, for example, the batteries against overvoltage or overcurrent. The traditional approach is that you have the batteries already available, the whole system, and that you take some uh, board where you will develop the software that will actually control it. So, for example, this will be the board that the designer will be using. This is used. It is quite a common approach, but there is one. Well, there are several disadvantages of this approach. One of them is that at the time that you start the development of your controller, uh, you need to have already available the rest of the system. So you need to have all the batteries, all needs to be connected, installed, and so on. So it requires that someone, or you or someone else, will make the whole device and give it to you for, let's say, for playing, so for development of the algorithm or the hardware. The second disadvantage is that if something changes in the assignment, for example, you need larger batteries, you need larger powers, and so on, then you need to rework all this electrical system so that it fits what you have changed. And the last disadvantage is that if you make an error, or if you have some problem during the development, then if you are working with the real system, it can be damaged, and you could, for example, burn the batteries, you could burn the electronics if your controller is not working properly. And this is again quite common in the design stage because you need to be very careful about currents and voltages and so forth. So the hardware in the loop approach will try to eliminate at least some of those disadvantages. And it's working like this. You have a plant model. This is the model of your system. This is a mathematical model. So this runs somewhere on some PC or some on some other hardware, and this is really just a model. So this is basically what you have been doing right now. You have been creating the plant model, for example, the damping system, or the car model, or the airplane, and whatever that you've been assigned. And this plant model runs on some dedicated hardware. In our case, it was a PC, but in most hardware in the loop simulations, it is either dedicated PC or it's a special real-time machine. You can see it here. Maybe you can read it. They say performance real-time target machine. So this is a special PC that is doing nothing else than running the real-time model of your plant. So in this case, it will be running the battery model, which can be either described by differential equations, it can be described by just some logical equations, it can be described by transfer functions, and so on. It doesn't really matter how this is described, but this is a dynamic model, and you can, of course, run the model, and you can also visualize the performance of your system. So for example here you could see the voltages on individual cells in the model. You could see the currents, you could see state of charge, and so on. So this is a real-time target. In our case it was a PC which was doing something else as well, Windows and stuff. But for hardware in the loop, now this is typically like a standalone machine where it's just running the plant model. You need to communicate, of course, with the controller. And this is the controller of the battery management system. So in our case, this was the nuclear board, and it was sending data to the real-time model. In our case, it was only one way. So we have been sending data from the controller as a signal generator to the real-time target, and we've been getting only the, the step response. But in case of a hardware in the loop system, now this data will go both ways. So you will read some values from the plant, you will react somehow in the controller, and then you will send back some other data. So for example, if this would be the case of the plant of, let's say, ball on the beam system, or let me say maybe the inverted pendulum, doesn't really matter. I would read the position that I have from some sensor. I would send it through some line into the controller like that. Here I will perform the control algorithm, and I will send back how I want to change it. In case of a battery management system, you would read, for example, the voltages on the individual cells. You will read the currents in the cells, and the controller will control it in such a way that, for example, it's charging all the cells correctly at the same time. So what we will be doing next is that we will see how to make this approach. So how to connect a real-time machine with your controller board, and I will show you a few, maybe I have like 15 examples of real-time devices used in the industry. Now in this picture you can see here that this basically is a really specialized hardware set. You can see here that they have special boards that actually emulate the batteries, and the reason why this is typically a specialized machine that is doing nothing else is the speed requirements. But at least for electrical systems, the calculation speed that you require is significant. Based on the plan that you have, it may be in the order of some microseconds or even smaller. If it is a mechanical system, like a damping or some car or something larger, then for mechanical systems, the inertia will typically filter out the necessity for fast changes. So it means that For mechanical systems, you can use much slower real-time devices, and it could be an ordinary PC. But if you want to simulate such an electrical system like a battery management system, then it will need to run much faster. So based on the requirements on your model, you need to select, or someone needs to select the let's say proper real-time machine, and they can be very expensive. It could be, I don't know, something like 10 million Czech crowns, or maybe more, because it will be very expensive, because it needs to be very fast as it works in real time. So then now we have a plant model created as a simulation, and here you have your board that you are developing the code for. So this can be programmed in C, this can be again programmed in Simulink, for example. So then you have one code that runs as a controller, which is here in your board, and the second code runs in the real-time machine as your plan. And when you have developed correctly the control algorithm for your controller, what you can do is that you can unplug the board, the controller, from your hardware in the loop system, from this real-time target, and you can plug it into the real system, and you don't risk so many problems with damaging the device just because your controller is already tested, at least with the model of your device. So today in many industrial areas, this is the typical approach. You or someone else will create the mathematical model of your plant, then it is implemented on a real-time target, then someone else will develop the code for the controller, and in the meantime someone else can build the real device, and then when the development of the controller is finished, it can be tested including the real system with this model, with this development board. Not development board, but your controller board. So this speeds up the design process because it does not need to be serial. Someone needed to develop the device and then the controller and so on. And now some tasks at least may run in parallel. So if you have the plant model, then you can run in parallel the development of the controller based on the model, and at the same time some other team may work on the real device. And also, of course, safety is an important factor, because if you are running the plant model, then you don't risk to destroy your plant because your controller will not work properly, for example. So in this case, you may prevent the battery damage, you may prevent large currents, larger voltages, and so on. For all cases that I will show you, here is always the source that where you can find additional info about those systems. So this was the first example of a battery management system. A second example, again from electronics, is a photovoltaic system where they have actually used this hardware in the loop approach to simulate the power grid and to develop the controller for the photovoltaic system. So you can see this set here on this picture. Here is a photovoltaic panel that is producing some electrical energy. This is this device under test, and it's producing DC voltage. Now this DC voltage is usually fed into the power grid. So from the inverter, it is going directly to the power grid. But if you want to develop that this works properly, you need to test it under many conditions. You need to test, for example, if it is able to deliver power regardless of the solar conditions. So if here you have a large solar density irradiation or lower, then you are basically developing a controller for this device, for this inverter. And with a hardware in the loop approach, what they have done here is that they have basically simulated this power grid as a very simple mathematical model, and you can see the model here in this part. So this is a simulated grid, AC power supply, this is the impedance of the grid, and this is a current supply. So all this you can describe with a differential equation. So this is basically the plant, and this simulated grid is running on the real-time target. So if you are developing this controller, you basically feeding the current from the converter like a signal. So here you see this red path. This is telling me that the converter current is going somewhere, but this is a simulated signal. In the real app, it will go to a sensor that will measure the real current in the circuit, and then this will convert the analog signal from the sensor into a digital one. So from this, like this part is the card that is in a PC, for example, and that you have an AD converter and a DA converter. Now this is the real-time model. This is similar to the model that you have been doing. So here this is a simple grid model. They filter out the input signal to eliminate some noise, and then they feed it into the model. So in the model, they are the input of their model is the AC current that the inverter is producing, which we have here. Now they simulate how the grid will react to this input current, and the output for them is the voltage of the grid. So for example, a very simple case is that if this would be a very large power plant, now you start feeding some current into the network, and the voltage in the network will increase. And then this is the input for your controller, for your inverter. So they produce an analog signal, and this is the input voltage that they feed into the inverter. So like this, you can test this electronic inverter or all its functionalities without actually connecting it directly to the grid, so that you don't risk basically anything. You just simulate the grid, you develop your control algorithm properly for the inverter, and then you're sure that well, you have much larger probability that you will not destroy all your devices if you connect it directly to the power network. Obviously this example is again an electrical system, so it will require that the sampling frequency of the real-time system is quite high, because here you are basically simulating the power grid, which is an electrical system, and it will have a very small time constant. So again, in electrical systems, it's typical that this is the dedicated hardware which runs at a very high speed. Uh, a very similar example you can find on this link, and in this application they have used the hardware in the loop approach to protect some appliances from the power grid. By some appliances, I mean, for example, here you can see an example of a power plant. So what will happen if there is some problem in the power grid that you have here, or what will happen if you have some problem in the generator of your your wind power plant. So again, here this is a very simplified mathematical model of the power grid. You have some source, you have some load here. This is the generator, and by using the models and not the real hardware directly, you are able to eliminate many problems during the development of your control algorithms. There is actually a video that describes this. I think you can watch it yourself. I will not learn the videos. The fourth example is control of electric machines. So imagine that, for example, you are asked to develop a controller for some electric car. So someone will give you the mechanics, someone will give you the power electronics like this, and your task is to create the control algorithms. So you can see here that again, this is not like a fictional example. This is from some seminar based on some real case, real world scenario. And here the task was to develop the controller that will control the electric motor in such a hybrid or electric car. And of course you need to perform many tests before you put your product on the market. So it's not just that you connect everything, you program it so that it works, but you need also to test it for different problems that may happen the in the lifetime of your product. So what they have done here is that you can see here this is a traction motor that drives the wheels of this car. This was by the way, a hybrid vehicle. So here you have a starter generator which is powered by a combustion engine. Those two blocks, that's the frequency inverter, and basically here you can see the battery, and you can see the converter that can convert the energy from the generator to the battery, and from the battery to the traction motor. What they have tested here is, for example, what will happen with the controller and how will it react if you have a fault on one phase of the electric machine. So this is a three-phase machine, but what will happen if for some reason the wire between the inverter and between the synchronous motor of the electric car will be disconnected? So the controller needs to be ready for this. It will either shut down, or can it still be functional under some conditions with limited power and so on. So here, this is where the hardware in the loop approach comes in play. You can of course do this in reality. You can install it on a dynamometer, and you can run the test, you can cut the wire and so on. But you can imagine that this would be fairly dangerous if you cut the live wire with a live current. So first you need to test properly what your controller will do, and how is it ready for all this. So what they have used here is a real-time target from a company that's called Opal RT, and they specialized on real-time devices, real-time targets, and you can see that this looks like this. So it's a specialized hardware device that runs the electrical simulation of your traction motor. This could be a model with differential equations. It includes the model of the inverter, which is in most cases like an easy or simpler mathematical description. It's typically not described by differential equations, but let's say logic conditions only. and the boost converter can either be modeled again with differential equations or just by simple logic. And the battery the same. It can be a complicated model with differential equations if you really need that model. And all this is then uploaded into this real-time target, and it runs at very high speed, maybe a few microseconds or less, sampling frequency. And you connect your controller, you develop your code for the controller. The controller basically thinks that it is talking directly to your system, to your inverter or to your electric machine, and you get the signals from the device, you get the speeds, you get the torques, you get the currents, and the output of the controller is how should I switch the transistors here, how should I handle the faults, and so on. So this is an approach that we are basically using on our department if we are developing some control algorithm for an electric machine. We don't have a device like this. We develop the controllers uh, which we run in real time on a device that you will see a bit later. But you can basically run the mathematical model also at the same time in the same hardware. Now let's see something a little bit different. Um, Nowadays it's quite popular to at least hear about autonomous cars, and obviously in autonomous cars you need to have a lot of testing with your controllers. So what they are using, and again you can take a look on this brief video how they are doing it, is that they are using the hardware in the loop simulator, which is basically this device. So this is the real-time target, and inside of this real-time target you can put the model of your plant. So for example, they have created the model of the car including some animation. You can put the model of your automotive components inside, so again a mathematical model, and this is the electronic controller unit which then controls the car. So it reads the sensors, it will steer the car, it will accelerate the car, it will brake the car. So uh, this is useful because you don't need to test the car directly on the road or on some test track. You have a mathematical model that runs first in a simulator. In the animation and on some charts you can see how well is your controller performing, and you can tune your controller, you can change the algorithm, you can use different calculation algorithms and so on. So uh, it's a very common approach to use this hardware in the loop in automotive, because you basically save the necessity to do it with a real car, with a real component. And this includes not only the autonomous cars, but it includes, of course, for example, combustion engine controller units. So in this case, this would be running a model of the combustion engine. It will give you some real signals, such as speed, such as torque, such as, for example, the exhaust gases, and those electrical signals are processed with the electronic control unit. It's doing something, it's telling the engine to accelerate or not to accelerate, and then this controller unit can be developed much safer than using it directly in a real device. Next example, you can use this similar approach also for development of sensors. So if you are, for example, developing a radar sensor, let's say you want to use this radar sensor in an autonomous car so that it measures the distance in front of the car and finds other cars on the road that are in front of you and will feed it to the controller system. So today's cars, they have many controller units. This ECU. ECU stands for electronic controller units. Actually here you can see multiple let's say simulators that we have in the system. So here this is the radar sensor that I want to test or that I'm developing. So I need to provide some input signal, and if I want to do the testing in the lab, I will have a problem how to get actually the signal. How do you get the signal from that simulates a car that is 50 meters from you? Well, you can go outside and you can measure it somehow, but you can also use an RF simulator. So now this produces an RF signal that you feed into the input of your sensor. You can see here radar sensor and GPS. So you can basically generate, let's call it a fake signal, and because this is software based, you can change it and you can simulate now that you want to test it for object that is 50 meters away or that is 100 meters away, or you can have snow, you can have fog and so on. So this basically fools the receiver, the radar here. Then your signal goes into the electronic control unit, and from here you may feed it into the simulator of your car, which may show you some scene of your car, how is it moving. You may simulate different conditions, different slopes, different obstacles on the road, and so on. Or what you could do is that you could connect it directly, and you could, for example, that be working on the development on this radar ECU. So then it will be connected directly. Now note that in this picture they are basically fusing several sensors together. So they have one ECU for the radar, they have one ECU for GPS, and they have another separate ECU for the camera. And in here they are inserting some fault, so they are able to simulate as well uh, what will happen if, for example, the camera has some fault, and how will this ECU uh, react to this if it is working properly or not. So that's the sensor for autonomous cars. Another example is if you are developing electronic control units. This is basically a controller that you can find at many places in the car, such as we have seen here. We have an ECU for radar, one ECU for camera, you may have an ECU for GPS, you may have an ECU that fuses all the data and so on. So you can see that there are many units in a modern car, and they are all interconnected somehow through some bus or through some communication lines. That's how they transfer the data. And again, in all cases for all ECUs, you may use the hardware in the loop approach so that you develop some model or sub-model of your plant to test the ECU with this model, and only when this testing is successful, then you can use it on a real system, on a real car, and test it even further. Okay, now here is such an example of such a the hardware-in-the-loop approach. In this example, they have been testing the board that you have as a driver available, so that you see correctly the speed, you see the RPM of the combustion engine, and so on. So here is the tested unit, and here you can see that this is a plant, this is the model that simulates the virtual car, the virtual combustion engine. So those signals that you get from the combustion engine, they are going into this board. You can see the speed, you can see the RPM, and here they have the inputs for this simulated engine. So you can see the steering wheel, you can see here the pedals for acceleration, for braking. So in automotive and also in aerospace, this hardware-in-the-loop approach is very common. Some more examples from automotive. Again, I recommend you to take a look on some of the videos down below. Here you can see such a simulation of a car driving. So this is like a real physical model, of course based on differential equations, but you can see an animation here, how the car is going on the car. Now this blue triangle, this is the signal from the sensor. Where can it see an obstacle, for example? You can see the control desk, how fast is it going, what is the RPM of the car, and so on and so on. And again, if you combine it with this, you can have a steering wheel, you can have accelerator, so that you have a real-time control. So all those systems run in real time. Okay, some more automotive examples. If someone is developing the algorithms for autonomous parking, then again it needs testing. First, simulation testing before you run it on real hardware. So on this link that I have shown in the description, you can take a look on such a video. So this is like a real-time simulator where they have a car model. It's running on a system that's called DSpace. This is another, let's say, commercial name for a real-time target, and they are running a model of sensors in the car, and how can this car park on its own to some free parking space. So they have a model here of the sensors that you can see. This is the range of the sensor, this is the angle where the sensor can actually see something, and they have been using it for testing of those algorithms. Okay, now something from, let's say, aerospace. I found a nice example, nice video example of hardware-in-the-loop simulation that they've been doing in Brazil, and they've used this simulator to control the flight of a missile. Now, obviously, if you develop such an algorithm, you need to develop it first in simulation, because if you would test it directly on the missile, it would be very, very expensive. You fire the missile and you find out that your controller is not working. So what they've been doing is that they have created such a hardware simulator of the missile, so that it can control the surfaces and it can guide the missile. And in there they have tested what's required, and only then, when everything was fine, they have been testing the missile in flight. So in aerospace, it's even more strict than in automotive. In automotive, basically, your car can crash, but it will stay on ground. But if you're playing with such, let's say, missiles or airplanes, then you can crush your airplane or you can crush your missile. So hardware in the loop is very convenient because you basically have a model, mathematical model for your plant, for your missile, for your aircraft, and then you can test first all in simulation. Uh, let's go back to power electronics and electric machines. What you can see here is a simulation of a three-phase system. It could be an electric motor, for example, and this is shown here in this part. This is the model of the electric machine. This is the frequency inverter, and this is the power supply, which typically provides something like 650 volts. And the output of this device, of this inverter, you can see here, this is the voltage on the phase lines that we have here, and this is the current that we have there. And in this example, they are using it as a simulator for an electric machine, so you can change the DC voltage on the input and see how the system reacts. Basically, it's about how to control this power electronic part in some range of voltages, for example. And they can change the PWM frequency. This, of course, has an impact on losses. And they can change, of course, the parameters of the model here, the inductors, and all those components in there. Opal RT, I was already talking about it. It's a company specialized in doing simulations of electrical systems, and by looking on this picture you can maybe guess that it will need to be very fast. So the reason for this is that if you take a look here, you have a PWM frequency of let's say 1500 Hertz. So you need to calculate your currents at least with this speed, but typically much faster. So if you are simulating electrical machines and power electronics, the real-time systems needs to be very fast, in the order of at least few microseconds or less, and they are very expensive. This is such an example where they have used this hardware-in-the-loop approach to develop power electronics. I don't know exactly what they have been developing here. We may take a look on the video. But again, power electronics is one large area where such a simulation is quite useful. You don't risk any fire, for example, if your controller is not working properly. What we are doing, me and my colleagues, is the control of electric machines. And this is not our example, but we're doing something similar. We are basically developing the control algorithms that we put in some device as a controller for the electric motor. So this is the electric motor, and you can run a model of the electric motor, including some animation, and then you have some signal that you feed back into the processor or in some other device, and this is the control that you are developing. So control of electric machines is what we are doing on the department. Few more examples. I think there are like 2 or 3 more. Some nice examples that I found in some videos or application notes. This is an example of stability control. So for example, you can have a car model here. You can see that this is like a really complex model that encapsulates all the mechanics of the car. But if we look inside, they have used a model of the suspension assembly, like of the whole assembly that you may see here in the model. You may see that here they have created a model just of a particular system in the suspension set. And the inputs to this model will be, for example, the uneven surface of the road. That was one of the project that I gave you. So you can study with this approach. If there is some uneven road, how will it affect the suspension system, and how will it affect the car and the driver, and how effective is the suspension system? How can I tune it? How can I improve the suspension and so on? So I don't need to test it in reality on the road, but I can feed some arbitrary signals on my input of the car as the road input, and I can study with the model that runs in real time what is happening with the car and with the driver. Uh, this was also one interesting example that was from Czech Republic, from the company Škoda, but not the one that builds cars, but there is another Škoda that builds trains. And in this example, they have been describing how did they use the hardware in the loop approach to develop a control system for a locomotive, so for a train. So you can see here that this is the control system that they are using in a real locomotive. They are feeding in some signals that basically fool the ECU so that it thinks it is in a real train. They are doing this with those interfaces, which is not important at all, but this is the simulator that runs the testing. And in this simulator, they will have a mathematical model of your of the locomotive, so that this ECU thinks it's connected to a real locomotive, and they can test everything directly on a bench, and they do not need to connect it to the real locomotive. They may test different speeds, they may test limits, in what ranges is it working, and so forth. So in our labs, in our examples, we have a system that is similar to this one, PSI simulator, and we are actually using it in the reverse mode, well, not mode, but reverse direction. We are using this hardware to develop control algorithms for the power electronics that we are working on. Okay, and I think this is maybe the last example. You can use the hardware in the loop approach to test UAVs. For example, if you are developing an autopilot algorithm. So normally what you would do is that you take a remote like this, you send some data to your receiver in here, and you are trying to steer the model. But of course this could be quite dangerous if your autopilot is still not fully working. So it could crash, it could fly away, and so on. So here you can see that they have used a simulator, and in here we can see why it might be so complicated, because they have one PC that is dedicated for flight dynamics simulator, because this needs to simulate the complete airplane model in 6 degrees of freedom, which you can see here. And of course it's a non-linear model, so this will require a high performance in calculations. The signal is coming in from the autopilot, if it should steer the plane, or how should it steer it. So this would be a third PC, probably, or four PC that simulates the autopilot. This is what you are developing. Your input signal is the signal from the receiver. The autopilot talks with the real signals, well, not real, but let's say simulated signals with the flight dynamics here. So what is the tilt of the airplane, what is the yaw, what is the speed, and so on. And here they have a next other computer that is showing how this plane is reacting. So they have an animation where uh, they are sending the data from the flight dynamics, and they can see how the aircraft is flying. So when this is developed, when they have the autopilot developed, tested with the dynamics of the plane, they can take this autopilot, put it in some hardware, and they can continue with the testing in the real airplane. Okay, this is the very last example that I found quite interesting. A simulator of a guided missile. So you can see here they have a small model of the guided missile. Now on this setup they can rotate it freely. So they can rotate it, well, this rotates it like that, this rotates it like this, and so on. So they basically have 6 degrees of freedom. And probably they have been developing the control algorithm for this guided missile, so that here they have some signal that they are trying to track, like some heat source or whatever. And this setup was used to develop the control algorithm for that. Okay, now in the second project, what you will do is that you will be assigned one plant model like this, and your task will be to develop the control algorithm for this. So what you will have to do is that you will have to implement the plant model, which will be similar to the one that you were given for project 1. This will run in Simulink, and this will run on the Nucleo board. And the Nucleo board will read the signals from the plant model, or maybe to tell it correctly, the plant model will send the data to the Nucleo board. The Nucleo board will run a control algorithm and then control the system with the data that it will send back. Again, the plant models will be similar to the ones you received for the project 1, but the difference now will be that this will communicate both ways. So this will read the signal from the serial line, will do in most cases a PID control, calculate the output, and then send it back to the serial line, and the plant model will run in real time. So, so far you have been using only one-way communication from the Nucleo to the plant, but in project 2 there will be both ways. I will assign you the plans and the assignments next week, because today I would like to show you one more topic which will be related to the project number 2. And one of the subtasks that you will solve in project 2 is that you will need to visualize your plant. And by visualizing the plant, maybe let me choose something. Maybe this is a good example. In here they have, of course, a very good animation of what is happening in the process. So it's running the mathematical model but then at the end they see a very nice animation of the car on the road. So of course you will not do this because this is quite complicated. But what you will do is that you will run a very simple simulation of your system. And in the remaining time, we have about 1 hour left, approximately, a little bit more. I will show you how to do it. So let me show you first what will be the outcome of your simulation or similar. So what we will learn today. Here in Simulink, I have one model of a plant. Now I have used a plant that's the ball on the beam. So if I now go to the assignment of your project 1, so it was this assignment number 2. So what is it doing is that I have a beam and I have a ball on the beam. And obviously if I have an angle alpha like this, the ball will go to the left like this and will fall down. If on the other hand alpha will be negative, so if the beam will face like this downwards, then the ball will go to the right. And this is what I was trying to simulate here. So this is a very simple model. In complexity, it is similar to the ones that you have been assigned for project 1. So here is my angle, this is my input to the model. Now this is the model itself. You can see I have some parameters and 2 integrators. And the output here is the position of the ball. So what I see here is that this is basically this coordinate, this distance r. And I have created this simply by implementing this mathematical model that we can see here as a differential equation. Now the input is the rod angle, and I have used this sequence. Now this sequence is telling me that at time 0 I have angle 0, at time 2 seconds I have still angle 0, but at 5 seconds I have 0.075. This angle is in radians. So here you can see how will the input of the ball change. And you can basically see it here as well. This is the sequence that I'm using as the input to my model. So from 0 to 2 seconds I have nothing. The ball will stay at the initial position, which by the way was angle 0. So I have here initial condition 0 for both integrators, so that initially the ball is staying at some given position and that it's not moving at all. So angle alpha is initially 0. Then I will change the angle like this to some angle. So I will tilt the platform to one side, and then I will change the angle to another angle, and this will tilt. You can see it is a zero negative angle, so it will tilt the platform in the opposite side, and then I will tilt it back to 0, and then it will stay 0. So what will happen in the model, and you can again guess what should be the outcome. I initially have the ball aligned in horizontal position. Now I apply positive alpha. The ball starts rolling to the left, and then I apply negative alpha, and the ball will roll to the right. And then if I move it back to 0, Since my model does not have any friction, it will not stop the ball and it will run away completely. And this is what you see here in this curve. This is the ball position from this scope. So this scope is the input of my model, and this scope is my output of the model. And what I want to show you today is how to make an animation like this. So let's start the model, and in this window, this figure, you will see how the ball is moving on the platform. So here this blue circle is my ball, and this represents the beam. So let's take a look on how this runs. You can see that now I'm tilting it, and I'm tilting it back, and I'm tilting it to 0, and since there is no friction in my model, it continues to run away. So let's run it again. First nothing, then tilt to one side, ball starts running, I then tilt it back, and the ball runs to the left. So this will be the outcome of our class today. So how to run the model like this, how to do it. I have uploaded all my files that we will require for this simulation in Moodle. So you can find it. There is one new tab for you, Visualize in Simulink, and you can download this archive, this zip file, and you can run it on your computer. So I will not write all the code, but I will explain to you what the code is doing so that you can adapt it to your project number 2. So let's take a look on how this model works. I'm using a MATLAB function here. So what this Simulink is doing is that I have one input, which will be the ball position. This is basically the coordinate of my ball here. And the other model, the other input, is my rod angle, so that I can tilt this as desired by the angle from my Simulink model. So this is a block that you can find in the library browser. So if I now open the library browser, you can find out that the MATLAB function is there, and we can drag it into my model. Let's see. So here is a MATLAB function, and I'm actually not using this normal MATLAB function, but I'm using the interpreted MATLAB function. So this function takes the input values from Simulink, calls some code that is written in there, and in my case I'm not using anything as the output. So I'm using this interpreted MATLAB function. Let's take a look on how this is configured. I have written actually a function that has this name: beam on ball on beam update and visualize. It's just an arbitrary name so that I can understand what this function is doing. So what this function is doing is that it will take this figure, which is created in MATLAB, and will update it. So it means it will change the position of the ball and change the position of the beam. And a little bit later we will take a look on how this function is actually written. What is it doing? Before we do that, we need to take a look on how we can actually start this model. I have left a note here that before you run this Simulink model, you need to run this M file. and I have called that ball on beam init sim. So this is a file that will initialize the simulation. So let's take a look first on what is in this file. I will open it in my MATLAB, and you can see here it's just those two lines. But behind those two lines we actually have more commands, obviously. The first is calling another M file that sets the parameters for my simulation. So if you open this file like this, you can see that here I'm defining the parameters of my system. So in my system, which is by the way based on this web page, I have those numbers. M is the mass of the ball. Well, I've chosen a very heavy ball of 1.1 kilograms. The reason is simple. If you choose the original numbers from this web page, then the system is very fast, and I would not be able to show you this animation. It would just run away, and it would be very fast. So I have changed basically this mass of the ball, and I have changed also the moment of inertia, so that the inertia, you can see, is by approximately 2 orders of magnitude larger, so that it stays on the beam, and we can see it here moving slowly. If we would use the original parameters, it would just move back and forth, and we would not see anything. So this is like a simple assignment with the parameters. So I'm using M, R, and other constants. And in Simulink, you can see here I'm using this this model. So basically this is the differential equation, all this. And here I have the mass, I have gravitational acceleration, moment of inertia, and so on. So this file just defines the parameters that we need for the simulation. And if we do not run it initially, then Simulink will tell you that it does not know those parameters and that you need to define that. So that's the first file. And the second file will actually prepare the figure for visualization. So it will prepare this figure like it is, you can see here, and it will place the ball in the middle, and it will keep the beam that is aligned. So let's take a look on how this second file is looking like. I will just run it so that we see that now if I have started that, I have the beam is in the middle, and this is aligned, as I told you. Now this file is looks like it's more complicated, but basically what is it doing is that it's creating two objects, and the objects are kept in memory, and then Simulink is calling those objects, and it's changing their coordinates. So, well, basically this part is just that it prepares the figure so that I see this figure first, and that this figure is ready for Simulink to plot. And you can see here I have chosen some axes, so some scales on my axis. I have chosen some view because I found it nice that this is like a 3D chart. So this is not like a rectangle, but this is really like a beam. And what I can do is, you can see here, okay, I can also rotate the chart like that, and I can look from different angles. So this is basically what this command is doing. Just by maybe trial and error, I have selected that this was a nice looking angle to look. And this sets, of course, the labels for the axis, so that I have X, Y, and Z in my chart, so that this is labeled like it should be. Then this part will create the ball, the sphere in my example. So it creates this blue ball that I have here in the middle. And if you look in the help of MATLAB, you can see that there is a command called sphere, but this will generate a so-called unit sphere, so that it has a unit size, so it's 1 and 1, the coordinates. So what I need to do is that I need to adjust the size of it, and I need to center the sphere in my picture. So what I have chosen is those coordinates of the center. So x coordinate is 0, y coordinate 0.05, and this is for the z coordinate. So that if I rotate it like this, you see that it's not exactly in the middle, but it is slightly on different coordinates. And the reason why in y it's not 0 is that if it would be 0, it will be in the middle of the beam and not on the surface. So this 0.05 is actually the thickness of the beam, but we'll see that a little bit later. And then I'm just using those, this command surf. This is basically plotting the sphere. And I plot the sphere at the coordinate which is given by this. This is the x coordinate, this is the y coordinate, and this is the z coordinate. And r is the radius of my sphere. And this is defined in the parameters. You can see here the radius of the ball. I have chosen it's 15 millimeters. So if I change my parameters here, my plot will update automatically, and I will have a different size of the ball, so that I don't need to change it manually in the code, but I can just change the parameters. And in there, the ball 1 will be the name of my object. So we can see here that for in workspace, I have now a ball, which is a type of surface, and this is like an object that I will use further in my code. So this creates a ball. If you will need it for your assignment, you can just copy this, and you can modify the coordinates, and you can modify the diameters, for example. And the second object that I will create is the beam. And for this, I will use a function that's called cubeplot, which is again just some function of MATLAB. And here are some input parameters. So what I'm basically doing is that I'm creating a beam that has these dimensions. This is the thickness, and this is the length. And since this function is centered, so it creates the beam from 0, from this in origin, to the left and to the right, which is symmetric. So this is why here I have chosen the L half of the beam. And at the end I name it beam. That will be my object. And now what I need to do is that I make those two objects global variables, so that they are available for other functions and for Simulink as well. So this is the keyword. I will create a global variable ball sub t, and beam sub t. So this is for the ball and this is for beam. And now I have used a function of MATLAB that's called HG transform, and the input to this function will be the ball. So here you can see it there. I'm taking the ball, which is my function here, well, my variable here, and I'm setting that this is a property of the ball sub t object, and we will use it later in the update code. And the same here I'm doing for the beam. So what this code is doing is that it creates two global variables here, ball sub t and beam sub t, and I will have them available later, and I can access the properties of those objects from some other code that I write. And the properties of this object are obviously the coordinates. So if for example I want to put the ball not at this position like 0 and 0, but I want to put it there, I would call this object and I will say set the position to x 0.5 and y 0, for example. So this is done on startup when I initialize the code, and all this basically creates the figure that we have here with the view, and in the memory in my workspace I have now those two objects defined. Now if I go back to Simulink, we can see that here I'm feeding some numbers into the MATLAB function, and here I have called this MATLAB function like that: beam on ball on beam update visualize, and the input is some variable u, and this variable u is an array, and here it has one signal and in there it has a second signal, and this is going into the function. So now at the very end, let's just take a look on this function, what we are calling, and this is in there. So this is a MATLAB function. You can see here the name and the input parameters. Now in the array that's called u, we will actually have two numbers. On one position we will have the rod angle, and on the second position we will have the position of the ball. So what I'm doing here is that I'm telling the code that now we should use the global variable that's called beam sub t. So this part is for the beam and this part is for the ball, and they have the same structure. If you remember something from mechanics, maybe kinematics, then you should be familiar with the term transformation matrix. Now, the transformation matrix is a tool that allows you to calculate, for example, the position of some point on let's say on a robot, for example, if you know the coordinates of the other components. And this is what I'm doing here. I'm creating a transformation matrix, and for the beam I know that it will be only a rotational matrix, because if you look in this picture here, if I want to change the position of the ball on the beam, then let's take a look on the picture from this side like that. I need to align it first. So let's say like this. And in my animation I have chosen that the point where the beam will rotate is the origin. So 0, 0 is where it will rotate. So this point will stay all the way the same, but this point can go down or up, and this point can go down or up. So if I want to rotate this beam, I will use a rotation matrix that is created with this function. So this means that I'm rotating it based on the z axis, which is now going into the screen. And my input is coming from Simulink, which is telling me what should be the angle of my beam. And since this is the second input here, then it is the second element of my array U. So this creates the rotation matrix, the transformation matrix. And then I can simply say, okay, take the object of the beam, apply the matrix operation, and use this rotation transformation matrix. So this command will recalculate the position of my object. And the draw now command will update the picture. So I could maybe even comment it out like this, because here I'm using it anyway, and maybe that would save me some time. But I have used it so that it's clear that this basically repeats for the second time for the ball. So these two lines, they recalculate the position of the beam, and they update the plot in my figure. And then here those two lines are doing the same for the ball. But now note that the ball is not rotating, but it is moving. So this transformation matrix will be a translation matrix, not a rotation matrix. And the inputs will be U1, which is coming from the ball position in there. And this is in x coordinate. This is the x coordinate, and the y coordinate is this one. And you can see it's u1, the x times sine of the beam. So this makes sure that the ball will appear to be sliding on the beam, and it will not move just to the left and to the right. So this will move the ball up and down with the same speed as the beam is moving. And then at the end I again update the figure, and the last line is there because Simulink needs to return some value as from the function, otherwise it will not work. So I have simply returned the same as the input, so some dummy value for Simulink that it will not stop with an error. So at the end, let me run it again. Let me just show you the plots. And if we run it, now we'll see again the animation here. The ball will move first to the right, like this. Now for some reason it's slow, and now it will move back to the left. And since there is no friction, it will keep on moving until it runs away from the beam. So this will be one of the subtasks that you will be doing in project number 2. So for your system that will be some planned, you should visualize it somehow. And you can of course use this as an example so that you don't need to start from scratch, but you can use the rectangle, you can use the ball, and so on in your system. And it does not have to be a 3D animation, but it can be a 2D animated system.